Okay. Now, the next problems are a little different. Thankfully, because my brain's a little fried with the calculator. How about yours? Okay, so let's look at this. How is this different? Oh, this has number 4 and number 5. I don't think that was supposed to happen. Number 4 is kind of short and sweet, isn't it? Given the same reactant concentrations, the reaction of carbon monoxide plus chlorine gives us COCl2 gas at 250 degrees Celsius. It is 1.5 times 10 to the 3. That's known as what, 15,000? Yeah, times faster, or times as fast as the same reaction at 150. So we've increased the temperature by 100 Celsius degrees. That's a whole bunch of doubling, isn't it? So what do they want me to do? They want me to calculate the activation energy for this reactions. All right, now these kinds of questions are asked by AP a lot. Something is as fast as, those sorts of things, which is going to force you to assign a value of 1 to somebody. So since this is a higher temperature than this, I would say that 1 is assigned to the 150 situation in degrees Celsius, and the 1.5 times 10 to the 3 times as fast as then is your multiplier. So what we're going to do now is actually put that in, but we got to convert these temperatures to Kelvin and make reciprocals. We're going to get a perfect R when we do this. So EA is still equal to minus the energy R times the slope. So I've just got to think about what I'm doing. L1 is going to be my temperature. Okay, so I want 1 over T in L1. And L2 is going to be ln of K. So I'm going to assign this K of 1, this K of 1.5 times 10 to the 3rd. This temperature was 150 plus 273. This one is 250 plus 273. So let's see how that looks in the calculator. Clear all my lists. Starting over here. So I don't make any errors. I'm going to do 150 and 250. Go to the top. I'm going to take everything in L1. I'm going to add the 273. I'm going to add the 0.15 too. And then I'm going to take the reciprocal. There. Okay, then I'm going to come over here, and I'm going to put in 1 and 1.5 second EE3. Then I'm going to take the natural log of both. Oops, didn't mean to hit second. ln. There we go, of second 2 for L2. And there I have it. That's going to be a perfect slope, isn't it? It's going to have a perfect R because 2 points defines a straight line. So we're going to have a perfect linear regression on this data. I'd prefer a third piece of information, but it is what it is. So if I run the linreg on this, stat, calc, for, enter, there's what I end up with. Very nice. Notice the perfect R. So the slope is going to be equal to negative 8.31 times the negative 16189.3 yada yada yada. Alright, so that means that I'm just going to ignore those negative signs. 8.31 times 16189, if I wrote it down properly, is going to be equal to 134.5. Let's call it 135. 135 kilojoules per mole for the activation energy. And what is the value of K when the temperature is 100? So you know X, agreed? It's an X value, and 373 is what it will be in Kelvin, and we need to take that to the -1. So I go to my graph, which is still set up at 1L2, but it's got the wrong stuff in it. I don't think I pasted. Checking something real quick. Okay, so I'm going to go ahead and paste that, run it again and paste it into y1. There. Now it's actually pasted in there. So leave that one alone. And I'm going to take this out. Clear? Okay, so now if I go zoom 9, there we go. Go figure, a perfect straight line through 2 points. Okay, so now I go second trace, and I know what x is. It's 373, but don't forget to take the reciprocal. And I got to go 2. Because I'm way outside my range. No? 150, 250. Yeah, my range is smaller. Okay, so zoom 3 to zoom out. Enter to make it happen. Repeat. Second, calculate. Enter. 373. Don't forget to take the reciprocal. There we go. So y equals ln of k, it's baby k, equals negative 5.14, but remember it's stored. Therefore, k equals second quit, second ln. Get that y value by going alpha 1. And we get 5.83 times 10 to the negative 1, 2, 3. 5.83 times 10 to the negative 3. And amazingly enough, that is a correct answer.